Hello, everybody. Thank you for attending the second webinar of our lighting webinar series. Today we'll be talking about color. Today we are going to talk about the wavelengths and how we use that in machine vision to create a lot of contrast. So this is the light spectrum. The short end is UV light and it goes all the way up to IR light. The visible length is between about 380 to 780 nanometers. That's the average of kind of what people can see. Some can see more, some can see less, but that's roughly what we go by. And today we are going to be focusing on just visible light. So all LEDs will come with a spectrum similar to this, and they'll have a peak wavelength, and then they'll have kind of a range that they also emit. So for example, a green light, this specific green LED, has a peak wavelength of 525 nanometers, but it really emits between about 500 to about 560 nanometers. So every light, every LED will have some type of curve to show you where the peak is and what the spectrum curve looks like. So before we get started in how light works in machine vision, we have to understand what color is and why we see color. So the reason we see color is because that is the wavelength that a certain object reflects. So every object has certain properties. It will absorb some light and reflect other. So if I shine white light, or sunlight is the best light we have, it's got a very full spectrum, onto an object. If it's a red object, it is going to absorb that green and blue light and reflect that red light back to me. And that's why I see red. Same for green, same for blue. So if I use a monochrome camera where it removes the color, it just looks at the light that's hitting the camera, all of those samples are reflecting this equal amount of light, so they're all going to appear the same color gray to my monochrome camera. So what happens if I just shine red light onto my objects? Well, that red light is going to continue reflecting that red object is going to continue reflecting that red light, but the green and the blue object, they're going to continue absorbing that red light, and they no longer have green or blue light to reflect. So they're only absorbing, they're not reflecting anything. So when I now look through my monochrome camera, my red object is still bright, still that light gray, but the green and the blue object, they have no light that they're reflecting, so to the camera, it's not seeing light there, it appears very dark. So this is how we actually create contrast with a monochrome camera and using different color light and shining it on our samples. So just kind of another real world example. Here are some M&Ms. They have like your kind of basic colors here. If I shine a white light, you can see the orange, the green, and the red are all that similar gray. Maybe blue and yellow are a little lighter and brown's a little darker, as we would typically expect. But if I shine a red light, that red M&M, the orange M&M, and the yellow M&M all are bright. They're all reflecting that red light still, but the green and the blue are absorbing that light, and they're not reflecting any light. There's no green or blue wavelength there, so they appear much darker to the camera. And same for green. Now the green is reflecting the light, and the yellow and even the blue is reflecting a little bit of the green light, but much more than it did the red. And that blue light is reflecting, that blue M&M is reflecting that blue light a lot, and every other M&M is just absorbing that blue light, so it is appearing very, very dark to the camera. So this is a great way to create contrast with different colors and kind of see how that works in person. So how do we know which color to use when we want to lighten or darken a certain contrast, a certain shade? We can look at the color wheel. So anything that is a like color or family will lighten. So when I turned on that red light, my orange M&M and the yellow M&M, they all got brighter, but the blue and the green M&Ms, they got darker. And same when I turned on that blue M&M, that really darkened up that yellow M&M. It looked as dark as the brown one did in that situation. So anything across from the color wheel will darken it. Anything close to it will lighten it. Here's another example. I'm going to treat it kind of like a quiz, so feel free to answer in the chat or answer in your head. No one's going to hold you accountable, just play along. But this is just a sticker. It's got some red and yellow background, red text on it. And here's what it looks like with a white light. So of the three images here, left, middle, and right, which one do you think is taken with a red light? Yes, this middle one here. And we can tell that because of this red text here, it's lightened so much that it's actually disappeared to the camera. So that's how we can tell that this is red, because it didn't darken like the other images. So which one is the blue light? Correct, this one here, because we can see that this yellow darkens. So if we're going to darken, we look to the opposite side of the color wheel, and that is blue, and that's why this is so dark. And last but not least, which is green, this last guy on the right, and we can again tell that this isn't red because it didn't lighten this red text, it darkened it. So which light do we want to use? It depends on the application we're doing. If we're trying to read a barcode, probably red light is best. If we're trying to see the placement of the sticker and make sure it's in a good location, blue light is best. So depending on what we're trying to do will depend on the color of light that we go with. This I'm including as a real world application that we had, where we had to look at the bottom date code of some gummies. Here's like a little preview of the next advanced wavelength webinar. The IR light actually removes the text altogether and also lightens up the gummies. But more importantly, the blue and the green, they darken those red gummies. I can still read the date code, there's still contrast, but it's not nearly as much contrast as the red can create. By lightening those gummies behind it, I get more contrast here. But you can still read the date code, so this is probably an example where even if you don't pick the perfect red light, you can still get by and still solve the application. It's just made slightly easier by having the right color light. So actually that's it. It's very straightforward how we utilize color and what we do by just looking at the color wheel. We also can incorporate filters with the color. So I want to talk about what filters are and when the best time to use them is. So there are three kinds of filters. There's a bandpass filter, which will take the same thing as the LED had, where it had that spectrum curve. A bandpass filter has the same thing. It has a peak wavelength that it passes through, but then it has a range as well. So if you had a green bandpass filter, it would be 525 nanometers, but still allow light through. That's between 550 or 500 and 560, but it's going to block any light that is not within that range. A short pass filter is essentially drawing a line at 525 nanometers and saying, I will let anything shorter than this length through, but I will block anything longer than it. And then a long pass filter is just the exact opposite. You draw your line of whatever your peak wavelength is and say, I will block anything shorter, but I will let anything longer pass through. And any filter you come across other than a polarizer is going to fit within one of these three types of filters. So why do we use filters? What's the point of them? They have a few uses that I'll talk through. The first one is they are great at removing ambient light. I'm sure most of you have had applications where you set it up, you move it to a manufacturing site, you have a bright light overhead, it causes problems, or a window right by the machine that if it's sunny on Tuesday morning, it's not going to work. If it rains on Thursday, it's not going to work. A lot of times that is the issue of ambient light. So if your sample permits using a color light, it won't change the image too much. You can put a red light on or a blue light and then the same bandpass filter. So now the only light that's going to get to the camera is the light that is within that certain range. That peak wavelength, if it's green, the 500 to 560. Any lights outside of that is going to be blocked. So even that overhead light, it might be very, very bright, but that filter is now blocking most of that light out because it's only letting a fraction of it through, and that fraction that is within that bandpass filter. So it's a great way to reduce the ambient light, remove it as kind of as best we can. Another way is to create contrast if you're using just a white light. So you can see here, if I shine a blue light onto these pins, I get my blue pins are a little lighter, the red's a little darker. But if I shine a white light down and use a blue filter, I'm going to get the same image. And it's the same principle of what's happening. I'm either shining a light that's got a peak wavelength and a range, or I'm blocking all other light except for that peak wavelength and that range. I utilize this a lot in my lab when doing testing. If I don't always have the right color light I'm looking for to check and see if the color is going to matter to my image, I always make sure that I at least have it in white and then I have a good filter set on hand so I can just swap out my filters and see if the color is going to matter or not. So if anyone's doing lab setting, I definitely recommend having a good set of filters to help determine if color matters. Here's just a few more examples of seeing it in person. This is a yellow background with white text with no filter, but if you put a blue bandpass filter where you're only letting blue light through, it's darkening that yellow, and we can read that date code and all that text very clear. Same here, it's got red and blue images, red and blue items. If one bandpass filter, it lightens my red and darkens my blue. The blue bandpass filter will darken my red and lighten my blue. So the next way that we use filters is actually kind of a trick. It works similar to removing ambient noise, and we use it to remove light noise. So this is for if you have a multiple camera setup situation, you're looking at something 360, and you notice that you're getting interfering light from the other camera's light. So camera 1 is looking at one side, but it's getting light from the camera 2's light. What you can do is the same way we do create ambient light. So in this situation, I have a blue light shining down and red light shining on the sides, and there's no filter. So let's say this is camera 1 and the blue light is camera 2. If I put a blue filter on camera 2, my camera 2 is now only seeing that blue light. It's now blocking the wavelength from the red. So this is no longer interfering with my image of my camera 2. And then on camera 1, I could put a red filter, and I will only see these hot spots, and I won't see that blue light overhead. So, if you have 3 cameras, your first one can be red lights and red filter, blue lights and blue filter, green lights and green filter. You won't have any lights really interfering with each other, or it'll be significantly reduced. So that's just kind of a trick that we've come across that we like to tell people about. So when Leo gave his presentation, he, at the end of it, went through the lights to be used to achieve the bright field and the dark field, dome light, coaxial, low angle, ring light, bar lights. But for color, we don't really have specific lights that works for, but most of our lights will come in multiple colors. They'll either be red, green, blue, or white. And the HPD2 and HPR2 can also come in full color options. So you'll have 3 channels that come out. One will be red, one will be blue, and one will be green. These are useful if you want to turn on multiple channels at one time and create kind of that cyan color or that orange color that you see. Or if you have multiple products that you make and one product will use a red light to create the contrast and the next product will use a blue light to create contrast, you can just set up your full color ring light. When you run the first product, turn on channel 1 for red. When you run the second product, turn on channel 2 for blue. So you don't have to change light, you don't have to change filter. It's very easy to just run your programs, run the parts right after each other. And one more thing I want to comment on about that is if you turn on all 3 channels, you will get a white light, but it will not have the same spectrum curve as a white LED that you can see here. It'll be a little bit different. So it'll look white to us, but it won't have the same curve. So you might get different results if you were to compare full color light with all channels on versus a white light. It might differ a little bit, so just keep that in mind. And the last thing I want to touch on is that every LED, which means every product, every company, has a specific wavelength. It's a specific peak wavelength that will vary between light types and companies. So our ring light might have a peak wavelength of 635. Another company's ring light might have a peak wavelength of 625. Most of the time, they're going to be within about 10 nanometers, give or take. And for us, it varies between even different products. Our ring light will use a different LED than our dome light does, etc. So it doesn't typically matter to people. Usually a red light's a red light and it's good enough. But if you do have a specific peak wavelength that you want, make sure to ask for, find this reference curve, and you'll be able to know if it's the right, or it'll tell you in the data sheet what the peak wavelength of the LED is. But otherwise, that's all the info I have on color. And now we will move to the lab to see a little bit more in-person testing. Thanks.
Hello, thank you for joining us for the lab portion of today's webinar. The first sample we are going to go through is looking at a blue scoop in a white protein powder and see which light will work best to determine the presence and absence of that scoop. So you can see here when I have it just with ambient light, the white light is creating some contrast, but I think we can create more by using the correct color. So if I plug in a blue light, you can see my image brightens a lot, but also that blue scoop turns very bright. It's actually reflecting a lot of that blue light coming down, So it is not a lot of contrast between the protein powder and that scoop. In this image, it would be very hard to determine reliably if that scoop was present or not, if it landed in different locations around the powder. If we step to a green light, you can see that there is slightly more contrast. It's still reflecting some blue light back, but there's a lot of green light that it's absorbing, so it did darken. This is a much better image, but I still think it can be improved. And the most contrast we can get is with a red light. So this red light is on pretty much the opposite side of the color wheel, so it's going to darken this blue scoop a lot. That blue scoop is absorbing all of that red light, and there's no blue for it to reflect back to the camera. So this image, there's a lot of contrast between the scoop and the powder. It would be a lot easier to detect the presence or absence of this stark contrast, giant black blob in the middle, if you will. So that is the first application. Pretty simple, just using a dome red light to make sure the scoop is present. The next application we have to inspect is looking at jars of peanut butter. So there are a few different colors. We've got red, blue, and a few orange ones. And to our eye, there's a lot of contrast. This doesn't seem like it should be a very difficult inspection. But you can see as I put it under, and I put on just a white ring light, for example, it actually reduces the contrast a good amount. The text seems to disappear a little bit, so this actually would not be a very good image to test with. You would not get reliable results. But if we can step up to a color light, and again, we'll step with our blue light first. And so this is not a good image. This is actually worse than the white because you can see this red cap, again, is absorbing all of that blue light. There's no red light to reflect back to lighten up that background to create the contrast. So if we go from blue to green, it's a little bit better. This text is maybe a little bit easier to read, but still, again, we can do better. And here is the red. You can see the image got a lot brighter because it's reflecting so much light back instead of absorbing it. And there is a lot more contrast on this image. This would be very reliable to test with, and very easy to continue to read the date and make sure it's printed correctly. Now, as you can see here, there are more jars of peanut butter, more different colors. So let's try blue next. So if we were to just buy a red ring light and say, hey, this will work for everything, whenever they go to run the blue crunchy peanut butter, they'd have a big problem. It is impossible to read this code with this image. Now, just for fun, I can plug the white light back in, and we can see how that will look. And this is actually even worse than the red lid was providing. So you can see now that definitely white light is not going to be what we need to solve this application. So let's step through the other colors. So we started with red. We already know that that is not a very good color. And if we go to green, this is about the same results as red is giving us. So the next we can do is do blue. And this is essentially the same results as the red light was giving the red cap. That blue light is reflecting all of that light back. There's a lot of contrast, and it would be very easy to reliably see this image. So this shows the benefits of having a full color ring light in certain applications. The first time they manufacture and print on the red cap, turn on channel 1 for your red light. And then the next time when they're printing the date code on the blue cap, just turn on channel 2 for your blue light. And then you don't have to change the light, you don't have to change the filter, but you can inspect any color that comes by. So next we have an orange cap. There's actually two slightly different orange colors. These guys are a little easier to inspect. Even with a blue light, they're still creating a lot of contrast. But if we step over to a green, maybe it's a little bit different in the way it reflects. And even a red light will create a lot of contrast as well. So there's a fair amount of contrast here. It's pretty easy to inspect. We can even try creating a similar color light, a kind of yellow light, by using red and green at the same time. The red and green at the same time, they're all producing a lot of contrast, so there's not really a large difference of one over the other. But that being said, the fact that you have the ability to inspect with red and green on, or just one or the other. It just makes this light even more flexible. So you can see here that it works for this color as well. So one light we were able to solve 4 different colors that a white ring light was not able to solve. So this is a perfect example of having a color light with a monochrome camera to have as much contrast as possible. Even with this blue light and a color camera, the dark color of text versus the dark blue background might make this hard to read. So to save time, I actually cut away while I changed my setup. All I did was lower my lights a little bit and replace my sample. The sample that we have here is a yellow text on white conditioner. And all we're doing is, again, reading the date code, but this time instead of having multiple color caps, we just have one yellow text. So you can see here, with no light, it's very hard to read. If I turn my red light on, it's actually nearly impossible to read this date code. And again, what's happening, that red light is reflecting, the yellow text is reflecting a lot of red light back to the camera. So it's appearing very light and blending in with the background of the conditioner. Next, I'll step to green. There is slightly more contrast. It's not perfect, but it is more readable. We're still having issues, though, with the recycling indent of the bottom of the bottle. So now, when I step to blue, there's a lot more contrast. That yellow is absorbing a lot of that. The yellow light is absorbing a lot of that blue light and not reflecting very much yellow, as they're on opposite sides of the color wheel. And so there's a lot more contrast than there was before. One thing to note is we are still seeing a lot of ambient light right here. This is caused from my overhead lights. So I do want to highlight the ability of utilizing a filter to remove ambient light. So right now I have a blue light on, and then I have a blue bandpass filter as well. So if I just add this, and you can see right away that it doesn't perfectly remove the ambient light, but it really reduces it and creates a higher contrast image just by adding a filter. So the difference in those 2 images, one was pretty much impossible to read, and now this one is a very good, reliable image that is easy to read. And as I mentioned before in the presentation, when you have situations where you have interfering light, a good way to get around that is by using this type of setup, a blue light with a blue filter on a camera. So if I had red interfering light from a different application, different camera coming through, I can shine it on my sample and my image won't change. So all this red light that should be flooding and changing my image is being blocked out by that filter, so there's no interference whatsoever. So I'll take away this filter here so you can really see how much that filter is changing our image. I'll even darken this a little. So when I do exactly as I did before, now this is completely flooded. So by just putting that filter with my blue light, my blue filter, I was able to increase the contrast of my image and remove interfering light from ambient light, and then if necessary, remove interfering light from a different camera or a different camera setup that is nearby. So when we talk about filters, this is what we mean. These are prime examples of what they can do and how they can help us in machine vision, especially with our color applications. Okay, as you can see, I cut away just to adjust my setup here. Instead of having the top-down setup I did before, I set up a backlight inspection. My camera's just looking straight through. We're inspecting a purple mouthwash just for the fill level of the mouthwash. So you can see that this is a pretty decent image. There's not necessarily much here that we can improve. There's a solid contrast between the black line, but if there were a lot of bubbles, that contrast might be a little bit harder to see, and we really would like to see if we could get that purple liquid any darker compared to the color of the bottle in the background of the light. So if you don't have other lights available, this is when I want to show how using filters can help you determine if a better color light will be better for your application. So I'm going to start by just using an orange filter and placing it over. And you can see that it did darken my image, so I'll just increase it a little bit. But it doesn't seem to look like it has increased the contrast of the fluid very much. So an orange light won't be very helpful. Now we'll start with a red light. And again, it increased or darkened it a bit. This seems to have maybe increased a little, but it's not a drastic change where a red light would be the clear answer here over a white. So if we do this and then do that, it's still a similar image. So if we step up to a blue filter, it's the same one we had before. It actually looks like there's a little bit less contrast than there was compared to just the white or the red. So now we should step to a green. This is actually our cyan filter. The bandpass is about 505. And you can see that this actually does a very good job creating more contrast than the other items did. It's definitely an improved image. Will the blue white light work? Yeah, it will. But is this a slightly better image that might make the inspection that much more reliable and save you that much more headache? Yes, I think it will. So using a green filter on a white backlight, and we're able to improve our image, improve that contrast. We even have another light green filter here that does also a good job at improving that contrast. I do like the cyan filter a little bit better, so I'll actually screw that one on. And then you can see exactly how the convenience of having a nice filter kit in your lab for when you're doing inspections. If you only have white lights, you can still achieve similar results to a full color light. And also, again, what a simple filter can do to just create a little bit more contrast within your image. So that's all I have for samples today. I hope this was clear and helping you realize the importance of using color and making sure you have the right color, as well as utilizing filters when it's needed. Now we'll move on to the question and answer portion. Thank you.